Kinetics is the study of the rate or speed of chemical reactions. The rate of a reaction is expressed in terms of the change in concentration of any reactant or any product and the change in time of the chemical reaction. The change in concentration is expressed in molarity. That's the most common unit used to express concentration in chemistry. And for the change in time, we use the unit second because most chemical reactions are really fast. So seconds is a reasonable unit of time here. Let's consider, for example, the reaction between N2 gas and H2 gas to produce NH3 gas. If we wanted to measure the rate of this particular reaction, we would have a lot of choices. So for measuring the rate and expressing the rate, we could choose to monitor any one of the three molecules in this reaction, and we could measure the rate of the reaction by measuring the loss or the use of either one of our reactants, the N2 gas or the H2 gas. Or we could also choose to measure and monitor the rate of the reaction by the formation or the gain of our product, the NH3 gas. And we would choose, when we were doing this type of experiment, we would just choose to monitor whichever reactant or product was the easiest for us to keep track of. Let's consider a more simple chemical reaction because this reaction, even though it looks pretty straightforward, is actually pretty difficult in terms of kinetics. So let's consider just a generic reaction where we have one reactant. We're just going to call it molecule A, and it converts into one product, molecule B. You might be wondering what type of reaction is that simple. It could be something like oxygen gas being converted to ozone gas, something like that, or Cl2 gas being converted into 2 atoms of chlorine. So something along these lines. We don't necessarily know what the stoichiometric coefficients are, but what we know is that we have one type of reactant and one type of product. So if we wanted to monitor and measure the rate of this reaction, we could do that by either monitoring the loss of our reactant A or monitoring the gain or the formation of our product B. If we graphed the change in concentration for the reactant A and the product B over time, so let's make a little graph here. This is going to be time of the chemical reaction, and over here this is going to be the concentration. If we were going to plot this, we could say we're starting with molecule A, which means that we're starting initially with a pretty high concentration of molecule A. We don't know what it is, but we know there's quite a bit of the A molecule present. And as the reaction proceeds over time, we know that the concentration of the A molecule is going to decrease because the A molecule is being reacted. We see this happens exponentially. So the concentration of A drops off pretty dramatically initially, and then it just kind of levels off over time. So this is our concentration of molecule A. Now for molecule B, our product, we're going to start this reaction out with no molecule B present at all. So I'm going to draw a little dot down here for molecule B. And as the reaction proceeds, molecule B is going to be formed. So we're going to see its concentration increase. And it's also going to form exponentially. So it's going to kind of follow the same shape of molecule A. So this is for B. Now we can understand the exponential shape of the loss of A and the formation of B. Initially, at the beginning of the reaction, when we have a lot of A molecules, the reaction proceeds really fast, and so A drops off pretty quickly. And then as we get towards the end of the reaction, when there are fewer A molecules present, the rate of the reaction slows down, and we see this kind of taper off. And same for B. Initially, the B molecule is being formed very quickly, so its concentration jumps up very fast at first, and then it just kind of stabilizes. If we wanted to actually calculate the rates of these reactions, so we're going to kind of write it next to their spot on the graph. If we wanted to calculate the rate of the reaction in terms of molecule A, we would just simply want to calculate the change in concentration of molecule A over the change in time. Now, first of all, I am missing something from this equation. I'm going to come back and add it later, so just kind of make a note of that this equation is not quite done. Also, I want to talk a little bit about the notation here. So for the change in time, delta, which represents time, we're talking about taking the final time, so this would be the end of the chemical reaction, and subtracting the initial time. And the initial time in a chemical reaction is typically 0, like we're starting at time equals 0. For the concentration, so first of all, the use of the square brackets here, which we have seen before, remember that is just simply used as a shorthand way of representing the molarity of whatever molecule is inside that bracket, so that's the molarity of A. The change in concentration of molecule A is going to be the final concentration of A, so A final, minus the initial concentration of A initial. And remember, again, this equation is not completely done. We're going to come back to it. Let's write a similar rate equation for molecule B, our product. So if we want to talk about the rate in terms of molecule B, again, we're looking at the change in concentration of molecule B over the change in time. And I'm going to write over here. Now you know that time is final minus initial. Let's also, though, write the change in concentration for molecule B is going to be the final concentration of molecule B minus the initial concentration of molecule B. So let's think a little bit about the numbers that we're going to get when we calculate delta A, delta B, and delta T. For delta T, we're going to be taking the final time minus the initial time. Maybe this reaction takes 100 seconds, so it's going to be 100 minus 0. Whatever it is, delta T is always going to be a positive number. The change in time is always going to be a positive number. Let's think about the same type of thing in terms of the change in concentration for B. So the B molecule, we're starting, B initial is going to be 0. We're starting with none of it. And whatever we end up with, it's something. Maybe it's a concentration of 5. So the change in concentration for B, the change in concentration for any one of our products is always going to be a big number minus typically 0. So this is also going to be a positive number. For the rate in terms of B, we're going to have a positive number divided by a positive number, and that's going to give us a positive rate, which is logical. Let's think about A now. For A, again, the changing time is, of course, going to be a positive number. For the change in concentration of A, the initial concentration of A is high, and the final concentration of A is low. So maybe initially we started out with 5 molar A, and we ended with just 1. That's going to give us a final concentration of 1 minus an initial concentration of 5. That's going to give us a negative number. So like maybe we have something like this for the rate. That gives us a negative rate, which isn't logical. So in order to get rid of that, to deal with that, for all of the reactant molecules, we're just going to add a negative sign in front of the delta whatever it is, delta A or delta whatever your reactants are. We're going to put a negative sign in front there, and that's going to deal with the fact that the concentration of our reactants are decreasing and their change is a negative number. So this negative sign, this is the last piece that we needed to add to this equation. And these are two expressions that you could use to calculate the rate of a chemical reaction.